So how can sound escape when even light itself cannot escape? What you're actually listening to is vibrations. You gotta hang on that object to get those data. Voyager 1 and Voyager 2 are only two examples of how crucial space probes are to our comprehension of the universe. These probes are supplying us with data on the furthest reaches of our solar system in real time, even though we may not have the opportunity to directly investigate them for many years. However, some odd data that the Voyager 1 probe is returning from deep space has NASA engineers stopped. What are the weird messages coming from deep space that Voyager 1 is sending? Is there a reason to be alarmed or not? Join us as we explore how Voyager 1 was touched by an unknown force in deep space. For nearly 45 years, the Voyager missions have played a crucial role in space research, giving some of the very first and most important looks into the real state of our solar system. The Voyager twin spacecraft from NASA have turned into time capsules for their generation. They have an 8-track tape recorder for data storage and about 3 million times less memory than modern cell phones. They also transmit data at a rate that is about 38,000 times slower than a 5G internet connection. The pioneers of space explorer operations are still the Voyagers. Our Sun and its planets sail through the galactic ocean known as interstellar space, which has never been investigated by any other probes. To acquire a fuller picture of our solar system and the interactions between the heliosphere and interstellar space, scientists are fusing data from early emissions with observations made by the Voyager spacecraft. No other spacecraft has been able to revolutionize our understanding of the Sun and its influence like these have. Every Voyager spacecraft acts as an ambassador for humanity, carrying a golden record with music recordings, greetings in a variety of languages, images of everyday life on Earth, and diagrams of basic scientific principles for anyone who might come into contact with the spacecraft. The record's gold coating serves as a cosmic message in a bottle. At the rate that gold corrodes and decays in space, the data will remain intact for more than 1 billion years. Experts have been astounded by the strength and direction of the interstellar magnetic field, and the new information has even sparked discussion concerning the shape and activity of the heliosphere, the Sun's magnetic domain. The heliosphere, long thought to resemble a comet, may really be more spherical than previously believed. And does it get bigger and smaller as sunspots appear and disappear, or does it stay mostly the same? In this investigation, the spacecraft has offered some tantalizing clues. Astronomers believe the interstellar medium begins when the solar wind, which is the flow of charged particles coming from the Sun, comes to an end. This plasma or ionized gas presses against the cooler, denser interstellar plasma flowing around it, acting like a pebble in a stream. Similar to how the top of the Earth's troposphere is referred to as the tropopause, and the heliosphere and heliopoles refers to the hollow cut out by the Sun, the heliopole's distance from Earth was a mystery to us when the spacecraft was launched. Considering that Jupiter is just 5 times further from the Sun than Earth, some have suggested that the heliopause could be located there. Estimates of the distance to the heliopoles increased as the spacecraft accelerated further outward. There is no doubt that it wasn't Jupiter, Saturn, Uranus, or Neptune. No one was aware of the precise location or time of Voyager's entry into heliopoles not long after it encountered Neptune in July 1992. To the researchers' results, despite being so weak as to be mistaken for a clean vacuum on Earth, the local interstellar medium is far denser than the outer heliosphere. The distance of the heliopoles from the Sun was also determined by knowing the estimated speed of the outward solar material and the time it took for it to reach the boundary. The distance of the heliopoles from the Sun was determined by knowing the estimated speed of the outward solar material and the time it took for it to reach the boundary. The average distance between the Sun and Earth is 1 astronomical unit, and this distance ranges from 116 to 177 astronomical units. On August 25, 2012, at a distance of 121.6 astronomical units, Voyager 1 crossed the heliopauls. There were a few obvious indicators that Voyager 1 had gone through the heliopause. High-energy solar wind particles started to evaporate, which was probably a sign that the rest of the solar wind had also been left behind. In addition, cosmic rays from beyond the solar system, which is partially obstructed by the heliosphere, intensified following Voyager's passage. However, many researchers were unconvinced by this evidence alone. There were two distinct problems. First, Voyager 1's plasma instrument had malfunctioned, preventing it from capturing the dramatic rise in particle density that happened when it left the heliosphere and reached into stellar space. Second, a different direction for the magnetic field to point toward beyond the heliosphere was predicted, but this did not materialize. The coincidence of the magnetic fields inside and outside the heliosphere has not yet been adequately explained. The Sun played a role in Voyager's success. Early in 2012, solar storms started to erupt, and the following year, they shocked the plasma that Voyager 1 was traversing. As a result, the plasma's electrons began to oscillate, which in turn led to the radio waves that the spacecraft was able to detect. These radio waves frequencies indicated that Voyager had entered a much denser area. 2018 saw Voyager 2 make its heliopauls crossing on November 5th. This time, there were no questions raised by the passage. The spacecraft's plasma instrument was in use and able to monitor the increase in particle density brought on by protons, electrons, and other charged particles colliding with it. It also noted the temperature, which was between 30,000 and 50,000 Kelvin, and was much greater than that of the neighboring interstellar medium. The plasma was probably compressed when it entered the heliosphere, which is why this happened. Similar to Voyager 1, the probe saw the solar wind diminish and the amount of extrasolar cosmic rays rise. However, the magnetic field did not reverse course, once more proving that the outcome from 6 years earlier was not an exception. The relatively close distances suggest that the heliopauls are stronger than previously thought. Voyages 1 and 2 are still traveling away from the heliosphere, whatever its precise shape may be. Since the spacecraft signals travel at the speed of light, it will take them more than 22 hours to get to us. When Pioneer 10 finally goes silent in late 2023, Voyager 2 will have traveled 129 astronomical units, and it will overtake it to become the second farthest spacecraft ever. The two voyages are traveling in opposing directions and are further off from Earth than any of them is. Scientists said that Voyager 1 had captured a humming sound that was connected to waves detected in minute quantities of gas located in the almost empty region between stars. The Voyagers lose power as the plutonium decays and produces less heat. Thanks for watching. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.